My name is Marlo Herring. I'm a research associate and PhD student at the Universität Hamburg in Germany. In this video, I would like to present our work with the title Automatically Matching Bug Reports with Related App Reviews. This is joint work together with my co-authors Christoph Stanek and my supervisor Walid Malesh. App developers face a competitive app market with more than 4 million apps. For the success of their apps, it is essential that developers adjust the apps to the user's needs and fix bugs timely. Previous research has shown that users' problem reports contain valuable information for app developers to detect and fix bugs. However, users and developers use different languages, and finding problem reports that match existing bug reports is challenging. On the one hand, software developers report technical bugs in issue trackers, and on the other hand, users often use non-technical and potentially imprecise language. Thereby, integrating the user's problem reports in the software development process can become time-consuming and error-prone. We addressed this problem and developed DeepMatcher. DeepMatcher is an automatic approach which matches bugs reports to related app reviews. So how does it work? DeepMatcher uses app reviews from the Google Play Store and bug reports from issue trackers. We first identify problem reports in app reviews. For this, we relied on our previous work in which we already developed the problem report classification. From the bug reports, we use the summary. Previous research has shown that the relevant information is already contained in the bug report summary. DeepMatcher then embeds both of these texts, and we yield two text embeddings, one for the problem report and one for the bug report. We then use the cosine similarity between these embeddings to rank the relation between the problem report and the bug report. In this example, the cosine similarity is 0.91, and we can see the problem report is related to the bug report. Let's take a closer look at the text embedding step. We embed the problem report and the bug report in the same way. We use Distilbert to compute contextualized state-of-the-art embeddings for each token, and Spacey's post tagger to identify the nouns within the text. We decided to consider only the nouns for the text embeddings to reduce the influence of frequent verbs such as crash, freeze, or hang. Spacey and Distilbert tokenize the text differently. Therefore, we map the tokens to each other to identify which Distilbert tokens are part of a noun. We then compute the sum of the embeddings, whereby we obtain our text represented as a vector. DeepMatcher further uses this vector to measure the similarity. For the evaluation of DeepMatcher, we collected app reviews and bug reports of 4 popular open-source Android apps from the Google Play Store: the Firefox browser, the VLC Media Player, the Signal Messenger, and Nextcloud. Each app uses its own issue tracker. For these 4 apps, we collected approximately 20,000 app reviews over a time period of 4 years. From the respective issue trackers, we collected approximately 40,000 bug reports over a time period of 9 years. We first automatically classified approximately 9,000 problem reports. We randomly sampled and verified these classifications until we reached 200 verified problem reports, 50 per app. DeepMatcher then suggested 3 bug reports for each problem report, whereby we obtained 600 suggestions. We then conducted a peer coding task for these 600 suggestions and identified 167 relevant matches. The average intercoder agreement for this task was 0.9. Let's take a look at the main results. We show the results for the hit ratio and the mean average precision for 1 and 3 DeepMatcher suggestions. The hit ratio is the share of problem reports for which DeepMatcher found at least one relevant match. Keep in mind that the mean average precision is a conservative score. It assumes that each problem report has at least as many relevant bug reports as DeepMatcher suggests. We found that DeepMatcher achieved the highest mean average precision of 0.73 and the highest hit ratio of 0.89 for Nextcloud. In contrast, VLC achieved the lowest scores with a mean average precision of 0.4 and a hit ratio of 0.51. Averaged over all apps, DeepMatcher achieved a mean average precision of 0.55 and a hit ratio of 0.71. These results provide evidence that DeepMatcher can find related bug reports for problem reports. Let's take a look at 4 further findings. For 91 problem reports, the 3 suggestions of DeepMatcher did not contain a related bug report. Therefore, we manually tried to find related bug reports and didn't find any in 47 cases. These cases are particularly interesting as they might reveal undetected bugs. Second, we found 35 matches for which the developers reported the bugs after the problem report was submitted. In these cases, the user's problem report might have been insightful and revealed an undetected bug first. Third, we found that the contextual embeddings are quite effective as they were able to reveal similarities between words like upload and synchronize, or download and save, or draining and consuming for the battery running time. Fourth, the language gaps between problem reports and bug reports differ for these 4 apps. We calculated their average similarity between app reviews and bug reports. We found that the VLC media player has the largest language gap as its bug reports contain technical names of libraries or codecs. In contrast, the language gap for the Nextcloud app was the smallest. The reason for this could be that the Nextcloud developers frequently ask their users to file a bug report in their issue tracker themselves. So we suggest the following application scenarios for DeepMatcher. First, DeepMatcher could identify problem reports for which we cannot find related bug reports. These problem reports might reveal undetected bugs early. This is particularly critical after an app update or a new release. Second, we can enhance bug reports with additional context information based on related problem reports. Or third, DeepMatcher's bug report embeddings could support the detection of similar or duplicates in bug reports, as we frequently found similar bug reports among DeepMatcher's suggestions. Alright, so let's summarize our work. We introduced DeepMatcher. DeepMatcher first extracts problem reports from app reviews and then identifies matching bug reports in an issue tracker. DeepMatcher supports development teams and integrates user feedback into the bug fixing process. Our results show that the DeepMatcher can help developers identify bugs earlier, enhance bug reports with the user feedback, and potentially lead to more precise ways to detect similar bug reports. If you have any further questions about our work, you can check out the preprint version of our paper, download our replication package, or directly get in touch with my co-authors or me. Thank you for your attention.
And we're back from behind the big coffee cup. How's your big coffee cup doing? That was a fabulous presentation. Thanks a lot. We have 2 of the authors here, Marlo and Walid. Welcome. And
hello.
I'm really curious to hear. By the way, can we congratulate Marlo? He just submitted his PhD thesis not too long ago, so congrats on that.
Thank you. Okay. Hope it's not too early. But
no, like you got to celebrate all the stages. You submitted the thing. That's what we're celebrating. We're not too early congratulating for your PhD.
Okay.
There'll be another party. So Rashmi says, great work. I was wondering if you got a chance to report the undetected bugs you found back to the developers.
Yeah, this is a good question. We haven't developed a fully fledged pipeline, so to say. So we didn't really apply our approach in a real world scenario or in something like a case study. The things we did were rather in an experimental setting. So we didn't show these undetected bugs yet to real developers. However, what we did is we ourselves took a look at problem reports that we couldn't match to any bug reports yet. And these were, so from our perspective, of course, we are not part of the developing team of this particular app, but from our perspective, they could be insightful. So
cool. Thank you.
Maybe I can add also something. I think it's definitely the next step to do, right? So this was kind of a controlled evaluation, and the next step is definitely, of course, to put it in a case or in a and of course this is nowadays a lot of open source developers are getting really annoyed by contacting them and asking them and giving them feedback. But if they go into that step, or if they respond, I think this would be really good to, of course, show them the result and say, hey, what do you think about this?
Yeah, I think that would be a great next step. Then we have another question here by Sridhar. Firstly, excellent presentation. A quick question. Bug reports require additional information for app developers, which usually is not present in app reviews. And how do you get that information?
Yeah, so getting this information and augmenting this information to a problem report would be the next step. So what we could do so far is, I think that Google provides in the background a little bit of information about feedback. So colleagues of mine already distinguish between implicit feedback and explicit feedback, and so this is a research field on its own, I would say. However, there are like sensors in an app that you could integrate to collect some data, how the user used the app so far. Yeah.
Maybe I also can add something.
Sure.
Actually, so this paper focused really on the matching, nothing else, not on the processing or summarization or extraction of the data. But there is another paper that we published recently at RE that exactly does what the question is asking. Basically, extract part of context information, basically 4 concrete context information. So the version number of the app, the version number of the platform, whether it's Android or iOS, and then simply whether this is affecting iOS or Android, and something else I forget. Anyway, but I can link I can add the link to the chat so that the people. So basically, exactly what the question is asking for.
Yeah, that would be great. Yeah, please add that one. Let's see. So while we wait for further questions to roll in, it's been 9 months since you submitted this paper. I bet, having known you for a few years, that you have been doing a ton of things in the meantime. So you want to give us a little inside scoop on what else you've been up to in addition to that other paper you're referring to?
Yeah, so my work was mainly about analyzing user comments and making sense out of them. And a step that we often do is like embedding text. And this is a really active field. BERT has outperformed many previous embedding procedures, and now within the past, like since we submitted this paper, there are new embedding steps, something like sentence BERT, for example, which was specifically trained for to embed the text into a vector that is designed to be compared with cosine similarity. So we used in this paper, we used DistillBERT, but there are now newer embedding steps which could be used and might lead to better performances if we would try it now with different embedding steps. Yeah, and the advantage there is that we would still stick to this bi-encoder approach. So also when we think about scaling this approach, this is really a good way how we do it currently, I would say, because we only have to embed each of these texts separately. We don't have to put a pair into the model and then get a result for this, but also we'd have similar ranks that we have to embed first, calculate the similarity, and then we get a result for this.
Good, cool, thank you. So I have my rubber duck here for consultation. whenever I run out of questions. And
Okay.
the one thing she was really curious about this morning was what the hardest part of this was. Like, what was the most difficult piece that you had to figure out for this particular piece of research?
The most difficult problem was, I would say, identifying these challenges, because so we had to deal with quite some challenges. The user's language is really prone to errors and lots of casual language, so to say, which is really difficult to map with this technical language that is in bug reports. Because there, of course, you spend more time and you have less abbreviations, and matching this is really difficult. So for the VLC media player, for example, we have in bug reports really technical terms, libraries, codec names. We don't directly find them, of course, in the user reports. Yeah, so this is for also spelling mistakes and things we could use and leverage the power of these text embeddings to overcome this. But this was really challenging, I would say.
Yeah,
So-
I mean that's the nice thing. Maybe I can also add something. Unless you have an urgent question, I can.
No, I have another question, but go ahead.
So that's the nice thing about the approach. So there are a couple of other use cases, as also Marlo presented in the presentation, and one of them is actually also to measure, or to at least visualize in the best way to measure these two different words, actually, you can say. So the vocabulary and the word of the user, and the vocabulary and the word of the developers, which is in the issue tracker, and the other one is online. And of course there are a couple of but it's still really a long way to go. So there is it's not really a tool right now. Yeah, so for instance, the other way around, it's not yet really solved. So we looked, mainly Marlo and Christoph looked at the way from the app reviews to the tickets, but the tickets from the tickets, or getting a ticket and identifying, so to say, in the App Store or the Twitter which fits to it, it's not yet so to say evaluated, not yet really researched. And of course, how it looks like exactly in the ticket system and the user experience or the developer experiences, it's also all still open. So
Okay. There is a not question in the chat that then does have a question mark, so I'm going to read it out anyways. As an app reviewer or end user, I would love feedback to say my review helped find and fix a bug. Do many app developers and teams often do that?
To my knowledge, I know that in the Google Play Store, there is this helpful score, or you can, but this is among users themselves, so this is another thing.
Right.
Developers can reply to app reviews, so this would be a functionality which exists, what developers could use. How often? So we found that Nextcloud only actively uses this, replying to app reviews, but this is not in place yet, I would say.
Yeah.
Okay.
I think it's an excellent question. So this is definitely only, like, most of the people are, and also in industry, in academia, both are looking at at most at users to get some information, so to say, but not to push back information or to give back feedback, I call this. So this cycle, of course, it is there in release notes and replying in app stores and so on. But it could be much more systematic. It could be, so to say, even in the app itself. And I think it's also still quite open, a long way to go also there.
Okay. We got 10 seconds left. This might be tight. Abdullah had another question. Main point from connecting issues between app review and bug report, but that's essentially the main point of your entire thing. I'm afraid we're out of time.